Hi, good day to all of you. This is Dr. Shiva here, and I would like to conduct with you one short session for one variable calculus. And today we will focus the technique of differentiation, supplement to your tutorial session, and this will be a pre-recording session. And this is also will be a complement to whatever you already learned in your what you call in lecture. Without further ado, let me start with the today's lesson called one variable calculus. Let me define what is one variable. One variable can be defined as a y equals to fx. This is a simple formulation to define the one variable, and over here you can see there is a one given independent variable, and here you can see this independent variable will be fit into one transformation function, where this function will transform the feeder x, one independent variable, into one or more than one dependent variable. But the most important things here, when we study one variable basically is explaining the one independent variable, the usage of one independent variable as a feeder to a functional transforming function to produce a dependent variable. And here you can see there is a one example called st. The t can be any concept in practical or in applications. It could be a time, or it can be any functions defining the parameters of real scenarios. Okay, now in the when we define one variable, definitely you will able to ask this question: what if there is a single variable, are there multiple variable as well? Yes. Therefore, what is multivariable? Multivariable is defining the same thing but in a extensive way, and this involves more than one variable. Sorry, I will put it that as a one independent variable. That's a very IV. Therefore, in this case again, we are giving a two feeder in the transformation function to produce one results. We call it as a outcome, and this is a dependent variable. And the examples can be any level, but it involves more than one variable, and it can be any complex formulation. Therefore, this one variable and multivariable will be extensively used in the differentiation. Now let me start with the techniques of differentiation, because before I define the differentiation, let me go to the word called calculus. The calculus, let me define the calculus. Calculus, in simple, calculus can be defined as a study about change. This change can be defined further as the change is basically caused by the time. The change basically, as you all know, change is basically caused by the time. Therefore, every time when we observe any changes, the changes will be related to the time, but time is not defined, or we won't be able to see physically to define the time. Therefore, this time first of all must be defined in a physical sense. Therefore, time can be defined as, it's not an exact definition again. This definition actually we are trying to define for the change. We are connecting the time to the change. Therefore, time is infinitesimally smallest event. That means in any progression, we are trying to divide the events into as smallest as possible, and it's an infinitesimally smallest. You must remember this is infinitesimally a smallest event, whereby you can observe the changes of any event as a smallest quantum unit, as a smallest quantum unit, as a quantum unit of changes or progress. This is what we are defining as a time. Now, therefore, calculus is basically a study about change, and this can be defined further with the word called change, and the change will be further can be explained as three concepts, and this concept will be explained in a later chapter. Therefore, I will not elaborate this topic into detail. Now, this change can be only precisely observed with the concept called limit, continuity, and the third one is differentiation. We call it limit, continuity, and differentiation. Whenever we see this, okay, differentiation. Therefore, differentiation. Therefore, you can see calculus is something we call it is a study about change, and the change is basically is caused by the time, and the change in mathematics we able to define as a limit, continuity, and differentiation. Now let me start very quickly, because as I say, this is a very short session, and the sessions will more emphasize on the techniques, and therefore this is a brief introductions to you before we move into the actual explanation of the techniques. Now this is because every one of you should able to explain very well when people ask you, okay, what is one variable, what you mean by calculus, can you explain something about the calculus? Okay, calculus, as I say, is a very extensive explanation is there, but we don't have much time to explain in detail. And now let me move into the techniques. Now, the techniques of differentiation, number 3, we will say the technique of differentiation. Before we move into technique of differentiation, let me explain to you the different representation of differentiation. Normally, the differentiation can be defined, or sometime when the definition in the symbolic representation, we will represent it in the prime. When we place some prime here, it's understood, it's basically we are differentiating the function, or sometime we use this as a y prime. this representation is basically introduced by the Lagrange, and there are some other representation as well to represent the differentiation. This is another technique. We will use f bracket y or dy dx, and can you guess who introduced this method? I know many of you will say Newton, but no, it's not introduced by Newton, and this is the representation of the we call Leibniz. Leibniz is one of the contributor of calculus, and is equally contributed to the calculus exactly as contribution of the Newton, and both of them produced their contribution at the same time for the calculus. Therefore, Leibniz is another contributor to the calculus world. Now, let me move further with the other representation, differentiation. We call it, this is a D, and we call any functions, and this is a representation of Euclid. Therefore, you can, if you see any books representing the representation differentiation with this representation, either it can be Lagrange, or it can be a Leibniz, it can be a Euclid method. Okay, now let me move further for the techniques. Techniques of differentiation. There are few techniques that which you should master before we proceed to the advanced calculus. Now, over here, let me introduce to you very quickly, because as I say, this is a very short session. I will not take too long. I just introduce some of the very important techniques, and I want every one of you master the skill of these techniques very well. In order to progress in the advanced calculus or the coming sessions, you should able to handle these techniques very well, and it's a kind of fundamental, and not only a fundamental, it's a compulsory. Okay, it's a compulsory to know these techniques in order to proceed to the higher level of calculus. Therefore, I want all of you to concentrate in this differentiation and master the skill of differentiation as much as possible. Okay, now let me introduce to you the first technique. As you all know, fx equals to c. Okay, c is a constant and fx is a one function, and the example can be a fx, and you can see there is a one single variable, but it's not changing anything. Here I place a one constant. When I differentiate this, I will get answer as a 0. Basically, the logics here that we are trying to derive based on the definition of the calculus, because in this case when we say there is a constant, it means the results is not changing in any circumstances. This constant means in any circumstances when the time progress, there is no changes taking place. If no changes taking place, when I try to differentiate, I can't differentiate that because no changes taking place. Therefore, what I'm trying to say in a layman or colloquial term, I may say C constant, I differentiate the constant, I will get no changes. This means no changes. See, no changes. okay, 0. This means it's a differentiation, no differentiation taking place, therefore I will call it 0. Therefore, when I differentiate number 1 or any constant value, I will get 0. Okay, I hope that you can understand this technique. It's a simple technique and one of the simplest technique that you can see in the differentiation. Okay, the next one is in any function. The next stage, I hope that you can follow. Okay, in this case, if in any function, we can divide that into the sub-functions like this. For example, I'll give you this as an example. For example, because I define it everything in another level of functions, because a function I'm trying to connect to the sub-functions here. See, fx, I put it here, for example, this is a constant, it can be a 5, 6, whatever, but I try to define it this as x2 plus 1. When you see this, there is a something c, constant never affect the results. Therefore, you can see when I try to differentiate this fx, therefore c, g, I need to differentiate the gx because this is a constant. Therefore, the differentiation directly you will differentiate not the constant, but the constant can be taken out, and gx, you need to differentiate the gx. Therefore, in this particular case, you can see the c will not get affected, therefore c will go out, and this is what you will get as a 2x. Okay, and we know we can move in, or sorry, maybe I can eliminate this, but okay, we will leave it because I hope that you can understand this example. It's a simple example. Okay, now let us move into the third example. Okay, I want every step of this you should able to handle very well, and for further examples, if you prefer more examples for this, you can see my I already uploaded in tutorial sessions. You can see examples with the answers. It's a very I have elaborated over there in detail, and you can see very extensive examples and many examples as well. Now the next one is rule of sum. Rule of sum. The rule of sum is basically involve more than two kind of functions. You can see I divided that into the two different functions. Imagine this is a functions I am representing with the two different functions, and it can be a plus minus, doesn't matter because you are using a basic operations here, and the examples simple. I'll just pick a simple examples for this, and this can be for example x and plus and or minus, doesn't matter. This is x, this can be x3. Okay, this is I'm just representing this as a x3, or plus 1 can be a plus 1. Okay, now you can see this I don't want to place here plus 1 because I wanted to show this the example here to say that two function representing two functions. Therefore, when you make a differentiation for this, okay, fx, this you differentiate exactly separately based on the sum. Okay, therefore it's a very interesting. This is one of the properties of the differentiation, whereby you can segregate the functions into separate. Therefore you can evaluate this separately and you can evaluate this separately. It can be a plus 1, no problem, because I wanted to show the single variable at least for you to see, oh, this is a function, this is how it works, this is a function, this is how it works. Okay, therefore when I differentiate this, I will get here 1 and it can be a plus minus, doesn't matter, as I say, and this will be x2. Okay, now this is you can see that I'm differentiating separately is possible. Now this is a simple, but it's a very useful function. Later you will see the usage of this rule of sum. And the next one is number 4. I think I will introduce as around 12 techniques. We will see how many we can go because it's a depend how do I going to define it the function. Okay, rule of product. Okay, rule of product is basically it's a fx gx hx. Okay, there are two functions in a product terms. This is when we define again is a two-way. First you need to define one functions here, f x. Okay, I differentiate that. First you what you supposed to do, you differentiate the gx first, then leave it as hx, don't disturb this, and because you are treating this as a kind of constant. Okay, we are treating this as a kind of constant. Okay, after we are treating this as a kind of constant, now for the next stage, for the plus, and we need to take this as a constant gx, and you need to differentiate that hx as a what you call you should able to differentiate the another hx. Okay, now the examples can be complex, but okay, you can say, sir, I can't see what are the two functions. Can be two different functions. Yes, there are many. For example, I choose g is as x. Over here I pick sine x. Okay, therefore you can see g can be represented with the gx, and sine is basically represented with the hx. Therefore in this particular case you can see this is, you can treat this as two different functions, and functions can be later we will see the trigo, the definition of the trigo for the differentiation. And here first of all you need to treat this as a constant, and then you differentiate this first. Therefore you will get it when you differentiate this x here, you will get x first. Therefore in this case you get a sine x. Okay, sine x. And in the second scenario you need to treat x as a constant. Okay, and the sine x you need to differentiate, therefore you will get cos x. Can you follow? Okay, because I'm this is a kind of revisions. I'm trying to give you a very short sessions, and therefore just to introduce to you the techniques. Okay, the techniques of differentiation. Okay, now the next one is a very important concept. Number 5, we call that as a rule of quotient. Okay, rule of quotient. Okay, what is rule of quotient? And again, the purpose I'm writing, I would like every one of you also take a pen and just copy. It's not like you see the the work that I'm doing here is not like a reading, or it's not like study the subjects. If you wanted to master the mathematics, I would prefer all of you to take a one pen and a paper, just copy. Okay, when you try to copy and you try to do by yourself, then only you will realize mathematics needs practice. Okay, and it's required you to practice, and you need to write. When you start write, then only you will learn the nitty-gritty of the mathematics techniques. Otherwise when you start read and I ask you to reproduce back the whole thing, then you won't be able to do it. Okay, therefore please take a one pen and pencil or whatever, a paper, and copy and follow. It's not a copy. Later I will give you some examples, then you try to follow and try to understand why every single works is producing this kind of results. Okay, later you can ask question. If you are not very sure, you can ask questions during the tutorial sessions. Okay, now rule of quotients. Rule of quotients works basically fx gx, okay, to hx. Okay, when you say this rule of quotient is a division, quotient means is a division. Okay, this basically is a definition. This definition is coming from the rule of product. Okay, you can change this to rule of product, whereby you can say this is a gx to fx and hx. Okay, now you differentiate this further, you will get rule of quotients. You see, I will try to define it here, g, and here fx and hx plus you can say this again. You treat hx as a fx as a constant, therefore you will get this. Now our intention here is to find what is f prime x. Alright, okay, you just manipulate this, you will get the gx hx minus gx h prime x divided by h to x. Therefore, the rule of quotients is actually derivational rule, basically using the product as a product rule as a solution. You can see that we are deriving the quotient rule based on the product rule. Now let me give you one example how to solve the quotient rule. One example, can I pick one simple examples for that? What is the best? Okay, I will choose some of the example here. Okay, why can I pick the complex? Okay, that doesn't matter, then I choose okay, take it as sign. Okay, we go for this. Okay, I choose the simple first, simple solutions here. Okay, this can be written as x. You can see here the sign x here. Then this is actually the purpose that I wanted to give. Okay, it doesn't matter. Okay, the basic rule here, first you need to get back to this one again. I want all of you to see this carefully. First, in order to differentiate in the quotient rule, whenever you wanted to use a gx divide by the hx and you differentiate that, first of all you need to differentiate the gx first, then after that you need to keep it this as a constant. Okay, keep it the quotient, the divisions here as a constant. After that minus, then again you retain gx as a constant and differentiate the hx, then you need to make it that hx as a power 2. Okay, now let us move. First you need to differentiate this, right? Therefore in this first case, okay, actually I wanted to show you this can be written as like this as well. Okay, it's not I wanted to differentiate, but I wanted to show you this. We can write this as x as this. That's why we can use a rule of product in this scenario to to solve the quotient rule as well. Now, when we use a quotient rule, the first thing here, you need to differentiate this. Therefore, you get a sine x minus, then the next thing you need to use x, leave it as x as a constant, and you need to change the cos x here. Okay, then after that, as a total solutions as a sin x power 2. Okay, this is very simple. Okay, I hope that many of you are able to solve this problem, this kind of problems. Is there so far? I think many of you are able to follow. Okay, now let me move to question number 5, then this number 6. Okay, number 6 is a chain rule, or we call it that as a chain rule or rule of composition. Okay, rule of composition. Okay, in the rule of composition, the idea of rule, why they call it this is a rule of composition or chain rule, because it's involved more than one functional transformation. You can see this from here, x moving into one, maybe I may call it h, and from that h we are moving to the, is using a one transformation function called h, and that from that h it moving to the another stage and is using a g. Therefore, in this particular case, if I say fx is equivalent to the g hx, if you see something, a kind of composition in any equations, you should be able to differentiate that in a simplest way. First, you differentiate that fx, and very, very important, you must differentiate the original g, first function, because you are here. Therefore, you should be able to only differentiate the g first. See, I differentiate the g first. I don't care what is inside. I just concentrate in the outside first. Therefore, I just differentiate the g first. After I differentiate the g, then only, you see, dot product, then only I will go to the next. See, first I will take this g first, I differentiate, then I will move on to the internal one. Okay, therefore I get a hx. Okay, this is for example, let me give you the example, because fx, you can see the g 2x2 plus 3. Okay, if someone to ask you to differentiate this differentiation works basically, we don't know what is g. Okay, we don't know what is g, doesn't matter, but we just differentiate that 2x2 plus 3 plus dot product. Okay, dot product, then only we should move inside, and you should be able to say that as a 4x. Okay, this is the second hx. Can you see this clearly? Now let me put it to you, what is g. Okay, if I start shooting the example with this kind of examples, like a sine and 2x2 plus 3, then what suppose you need to do, you need to differentiate the sine first. Okay, you can see the sine, therefore it's become cos 2x2 plus 3. Okay, after you differentiate the g, then only you should go inside and differentiate that. Can you follow? Okay, this is very important. This is a very fundamental and very basic, and this is most important as well, this example. Okay, because the rule of compositions, if you don't master the rule of composition, is very difficult for you to handle the advanced logics of differentiation. Now further, when I explain further, okay, maybe I call it this as A, example A. Let me move to the example B, which is I try to create more composition, okay, H, and inside maybe I'll try to make it this WX. There are 1, 2, okay. See, this means there are 1, 2, 3. Okay, here first WX. Okay, from the W we are moving to the H. From the H we are moving to G. Okay, can you see that there are few transformations or compositions taking place inside, whereby you can see is moving, okay, is progressing, is a sub into sub. Therefore, if how to differentiate this, again follow the same method, follow the same similar method. Here fx, when I differentiate, first of all what you're supposed to do, don't go and touch inside, don't touch inside, and first you need to handle the outside, okay, because from here you're moving, you see, you cannot directly go inside, okay, you can't do anything here because it's all composed, okay, it's a chain rule. Therefore first you must able to solve this G. Therefore G, okay, I W X, okay, after that concentrate inside, then you should able to handle that as a W X. Okay, once you have done the H, now you go inside further, okay, here prime. Can you see that? Okay, I started work on the outside, then after that I'm start moving into the second one, H. Now it's not finished yet, I need to go one step further, and this is how we can solve the problem. Can you see that? This is how we progress step by step inside. Okay, good. Is it a example? I haven't finished the okay, this can be a complex examples, but I haven't taught you this process yet. That's why, okay, we keep it this. Later I will give you some example for this in later portion. But okay, can you give a try for this? Okay, example, let me, if fx E, okay, E sine, okay, I just pick the same 2x2 plus 3. Okay, I haven't teach you this yet, okay, I haven't moved into this level yet, but let you give a try. Later I will explain to you this part, okay, this portion, because I need to teach you the exponential differentiation before I proceed to solve this problem. Okay, now can you give a try? Please give a try for this. Later we will try to come back and solve this. Okay, this is basically involving three functions. Can you see that? There are three functions involved here. I want you all to see these functions anyway. First, E contain what we call H. There is a sign, and inside the sign there is what we call H, W. Okay, you can see x2 plus 3. I want you to see there are three functions here. Okay, E, H as a sign, and this. Okay, therefore first you must follow. First you need to differentiate the E exponential. Later the second part you need to concentrate on this sign 2x2 plus 3. Then you need to move inside to this equation called 2x2 plus 3. Okay, therefore you want me to solve that? Okay, in any let me quickly put it to you, then at least you can see the results of this. In any differentiation, f ex gx, okay, when you differentiate back sorry, I don't want to put it that as okay, we wait, okay, because I need to elaborate this. Okay, this, I hope that please give a try for fx. We will get back here and to solve the exponential problem here. Now the next one is a very important one, which is a power rule. The power rule is number 5. Number 5 is a rule of power. Rule of power. Okay, the rule of power basically involving h, x, n. In any functions, if you differentiate that, you will get an end and hx n minus 1. This, sorry, if you, can you see that? Okay, if you, this is fx, hx and n minus 1, and this is, we call it as a rule of power. And the combination of the rule of power and rule